Our next presenter is Dr. Tommy Wood. He's an MD, PhD. His pedigree includes Oxford and Cambridge. And Tommy loves to challenge most things that his American physician compatriots like me say. So take it away, Tommy.
Thanks, Jeff. So I'll start by saying I have no conflicts of interest. So I basically want to start my talk by just mentioning context, and I think that's really important when we're talking about treating patients, treating clients, the context in which we're doing it. And most of my client-facing work is with an online clinic based in California, works with athletes. But we also have plenty of clients with chronic metabolic diseases, autoimmune diseases, increasing number of people with cognitive decline, which we know is directly related to metabolic disease. And in general, the people that we work with are very well informed. They've read all of your books, they've read all of your blogs, they've listened to all of your podcasts. They've often worked with multiple practitioners, and then when they come to us because something's not right, they've tried everything, and that usually includes a low carbohydrate diet. And so, like Jeffrey said, I think I've developed a bit of a reputation as a low carb antagonist, which I'm absolutely not, but it's because I spend most of my time trying to figure out why a low carb diet isn't working. And I think that this is really important both for people out there who contact me, maybe some people who have a high profile in the community, who have their weight loss is stalled on a low carbohydrate diet, maybe the coronary artery calcium score has worsened on a low carbohydrate diet. And what I'm going to talk about, I think, is very relevant just to metabolic disease in general. So I don't think that anybody here is really going to disagree when I say that carbohydrate restriction is or should be the first-line treatment for metabolic disease, and that could be obesity, type 2 diabetes, or basically any expression of insulin resistance, and we've heard even just today how successful that really can be. However, I do think that for some people, going onto a high-fat diet may continue to drive one of the main underlying causes of insulin resistance, which is gut-derived endotoxemia, which is basically toxins from bacteria in the gut, which then cause inflammation and insulin resistance. So when I first went down this path about a couple of years ago, I enlisted some colleagues, and we did what we call a root cause analysis, or from first principles approach, try and figure out the modifiable things we can do to try and improve insulin resistance, as you'll see here. And this is a very, very simplified version of a very big diagram, which I often show people and nobody can understand, so I've kind of stopped doing that. But the three things, the modifiable things that I think we can fix are cellular energy load, oxidative stress, and inflammation. And cellular energy load, that's what I like to call it, and this is basically determined by both diet quality and quantity, and there's a lot to do with the insulin load of the diet, as everybody here probably knows a lot about. However, oxidative stress and inflammation are both key determinants of cellular insulin resistance, and I know some people aren't really sure that this is very relevant to most people, so I think there's some nice examples. So particular oxidative stress, you may or may not know that when insulin resistance as a term was coined in the New England Journal by Howard Foote in 1929, he was talking about a case of hemochromatosis, which is obviously severe iron overload causing oxidative stress. This patient ate only 78 grams of carbohydrate a day and needed 1,680 units of insulin just to stay alive. I'm going to talk mainly about insulin today. We know that, inflammation today, and we know that when people are septic, they become acutely insulin resistant, and also people with autoimmune disease. Think of somebody with rheumatoid arthritis, they become insulin resistant, and if you manage to decrease their inflammatory burden, that insulin resistance resolves. And this ties really nicely into this very detailed paper that came out recently, and the press release that came with it was called "Every Meal Stimulates Inflammation." So they showed this. This is one of the first experiments they did, and they basically just took mice and they either fasted them, that's the white bar, or they gave them food, which is the orange bar. And then on the left-hand side, you see levels of interleukin-1 beta, which is just an inflammatory cytokine, and just the act of eating increases inflammation. And the reason they said that this happens is because feeding stimulates immunosurveillance, possibly to limit the dissemination of microorganisms contained in food. And this is actually really important because anytime we eat, we are exposing ourselves to the environment, and it's important that the body is ready to deal with anything that might turn up. But if we then want to try and model this, if we want to understand the mechanism, see if it's actually relevant to human metabolic disease, then we try and isolate the components, and one of the things we do is we inject something called LPS, or lipopolysaccharide, which is derived from bacteria. And here you'll see again fasted mice, white column. You just give them LPS, and you can basically recreate that same inflammatory response. So that allows us to then dig deeper into the mechanisms. So this is just a very brief overview. You'll probably know that there's two different broad types of bacteria, gram-negative and gram-positive, and that just is based on the color they go when you do a gram stain. So gram-positive go purple, gram-negative go pink. And you'll see on the right-hand side the Bacteroidetes, which is one type of gram-negative bacteria. They are thought to decrease in metabolic disease, so you might have heard of them before. But when we're worried about lipopolysaccharides, which you'll see here on the right in the small red box, they tend to come from a phylum of bacteria called proteobacteria. So it could be commensal bacteria we'd expect to see in the gut, like E. coli or Enterobacter, or some nastier things like Helicobacter, Citrobacter, and within this phylum you also have things like Yersinia, which causes plague, Salmonella, and things that cause gonorrhea and things like that. So some of the nastier bacteria can end up in this category. And the lipopolysaccharides are basically these tails that you see sticking up out of the pink membrane on the right-hand side. And as we try and understand inflammation and disease, what basically the main model that we use is we take E. coli, we take the LPS out of the membrane, and then we administer it either to animals or humans and see what happens. So I've done this in a number of different animals to look at particularly pediatric brain injury associated with inflammation. You can also inject larger doses and look at the effects to model the effects of sepsis. And increasingly, what people are doing is injecting small chronic amounts to try and model metabolic disease, and this creates something we call metabolic endotoxemia. And the reason this is important is that endotoxemia can just immediately cause insulin resistance. So you'll see on the left-hand side, LPS, it binds to its receptor, toll-like receptor 4 or TLR4, and then that goes and activates a number of kinases, which can then phosphorylate the insulin receptor and basically just stop the insulin receptor signaling. Then if you look down at the bottom, in the red box, NF-kappa B, you might have heard of that as a pro-inflammatory transcription factor. That increases the production of a number of, again, inflammatory cytokines, and relevant to this conference and everybody here, increase in something like IL-6 or TNF-alpha can cause leptin resistance, can decrease other adipokines like adiponectin. And it can also, if you have chronic NF-kappa B signaling, you could do things like inhibit autophagy, which we're all trying to do when we're fasting or exercising to try and increase the turnover of damaged proteins. So we know the mechanism behind it, but here's just a nice graph showing that. So if you take healthy human beings, on the y-axis you see the HOMA-IR, so that's just a measure of insulin resistance based on fasting glucose and insulin. 24 hours or 5 minutes before an LPS injection is somewhere between 1.5 and 2 on average. And then 24 hours after a single dose of LPS, that's increased by about 50%. And then if we look at population data, which I think is important if we're trying to bring together a conclusion here, this is from the FinRisk study. So this is 7,000 people in Finland as part of their MONICA study. And you see that on the left-hand side, this is fasting serum endotoxin, so the amount of endotoxin that people have circulating in their blood. And as you increase the number of positive parameters of metabolic syndrome you have a linear increase in the amount of endotoxin in your blood. And it's important to show that even healthy people who are completely normal do have some of this circulating around. It's not something we can completely eliminate, but this increase is very important and potentially mechanistically in terms of disease progression. So this is from that same study, but a different paper. And what they did is they basically put people into quartiles of fasting endotoxin in their blood. And the black line is people who have the 25% highest amount of LPS endotoxin in their blood, and over 10 years these guys have double the risk of any kind of heart event, and this is after they've adjusted for all the usual suspects like age, smoking, sex, cholesterol, all that stuff. So I've talked a little bit about fasting endotoxins, but just like insulin after a meal, which is much more predictive of metabolic disease, postprandial endotoxemia is actually much more important. So here we have a postprandial endotoxin in people with type 2 diabetes. And so the black line is just a normal healthy person after a test meal. And then the type 2 diabetic is the white bar. That's the percent above the normal healthy population. And you'll see particularly after 3 or 4 hours, right at the end, that's where you see that big increase in endotoxin. And what might be interesting to the audience here, particularly because we're a low-carb conference, is that the way that you do that, you induce a large increase in postprandial endotoxemia is by getting people to drink heavy cream. And I actually think you'd probably get the same thing if you had a nice big bulletproof coffee. So there's definitely an association there, I think we can believe, but that doesn't really mean that endotoxemia causes metabolic disease. It might just be an associated factor. So then we really want to try and dig down into this. And I think one of the most interesting things to look at is overfeeding studies, particularly overfeeding studies with a mixed or Western diet. We know that's probably the fastest way to induce insulin resistance. So if you overfeed somebody a Western diet, you can make them insulin resistant within a day if you do it properly, at least within a week. Now, interestingly, overfeeding also increases endotoxemia. So this is a graph. This is actually an 8-week study. They increased intake of butter, cheese, and almonds to increase calories by 800 per day for 8 weeks. And you see after then a test meal, the area under the curve for LPS, so the total amount of endotoxins that are getting into the blood tripled. And I know that's quite a long period of time, but there are other studies have shown that you can double the fasting endotoxins by just overfeeding for 4 days. So that's definitely within the same time period as we see insulin resistance in overfeeding studies. But if we really want to dig into the mechanism and see whether this is part of the initiating factors, sadly we have to go to animal work. So this is probably the most highly studied cited mouse study. And here you see endotoxin levels on the y-axis, and you have a control group just eating normal mouse chow. You have the high-fat diet group, which is the standard, very good at inducing insulin resistance and obesity in mice. And then to try and model the high-fat diet, the endotoxin levels, what they did is they put animals on a control diet, normal diet, and they just infused them with the amount of LPS just to make it the same as the amount of endotoxin you're getting from the high-fat diet. Then if you look at 8 weeks later, you look at fat. So visceral fat, the black bar is the LPS group. They have almost as much visceral fat as the high-fat diet guys. Not quite as much subcutaneous fat, but definitely more than the control group. Liver triglycerides, so fatty liver, increased almost as much as the high-fat diet group 2. And this is despite the LPS group eating just as many calories as the control group, which is half the amount of the high-fat diet group. So if anybody's thinking about increasing or a failure to reduce fatty liver, reduce fat stores despite cutting calories, they'll maybe identify with this here. So if you then actually look at the fat cells, this is really important because as we learn more and more about insulin resistance, we see that it probably starts in the adipose tissue, and it comes from the fat no longer being able to expand. So when your fat cells say, I've had enough, no more fat for me, thank you very much, that's then going to cause problems in the rest of the body. So if you look at the control group on the left, there's a normal, nice, healthy fat cells. In the middle, that's the high-fat diet group. So these are big, expanded adipocytes like you would expect to see in obesity. And on the right-hand side, you see the LPS group, and their fat cells are actually smaller. And this is despite the fact that these guys were more insulin resistant. So these fat cells are not willing to expand, and that's causing insulin resistance in the mouse. And the reason we get that insulin resistance in the fat cells is because of inflammation, particularly inflammatory macrophages, and that's what you see. That's that dark red staining around the fat cells. Those are inflammatory cells in the fat, then causing the fat to not be willing to expand, which then causes peripheral insulin resistance. So this is just a quick mock-up of how a Western diet can increase endotoxemia and result in insulin resistance. So there's endotoxemia, and the Western diet can basically cause this through 3 mechanisms. It can directly increase gut permeability. It can also increase LPS availability, and that's because refined fats and refined sugars are both very good at helping endotoxin get across the gut wall. The constituents of the diet can also cause a shift in the gut microbiota, so the microbiome of the gut, as well as inflammation in the gut caused by the diet, which then feeds certain subtypes of bacteria and particularly causes things like an overgrowth of E. coli, who love some of the byproducts of inflammation, grow really well on it, but then outcrowd some of the better bacteria that we want. And all of these can increase the movement of endotoxin from the gut into the blood. And so this is just a brief overview of the microbiome societal changes we see in metabolic disease. We definitely see an increase in pathogenic proteobacteria, like I talked about, but also a decrease in the beneficial bacteria. So bifidobacteria, you may have heard of, are really important and well associated with an integral gut lining. Akkermansia requires a healthy gut mucin layer, and that only happens if the gut is healthy. So if that's absent, then it's definitely an indicator that there's something wrong there. And other things butyrate producers people may have heard of, like rosiburiae or F-prausnitzii, which both produce butyrate, which feeds a healthy gut lining, but also feeds other beneficial bacteria. So that all happens in the context of a Western diet. So it's also really important to show that LPS actually directly increases insulin secretion. So if somebody's on a low carbohydrate diet and they're not seeing their fasting insulin come down, this could definitely be part of the reason. So this is just a plot of log insulin, fasting insulin on the bottom versus fasting endotoxin. And there's definitely a direct correlation between the two. If you do the inverse log of these insulin measures, it starts from about 4 to 25. And I think most people here would agree that a fasting insulin of 25 probably isn't a normal, healthy person. But it shows that across the range, there's definitely a correlation. And then if we go back to some mechanism in animals, we see that endotoxin increases glucose-stimulated insulin secretion. So here on the black line, normal control animals, insulin is on the y-axis. If you give them LPS and then give them basically a mini Kraft assay, give them some glucose, look at their insulin, you see a dramatic increase in insulin production. But this is definitely an inflammatory process, because if you give an interleukin-1 receptor antagonist, so you suppress the inflammatory response, then that insulin secretion doesn't happen. And this seems to be because hyperinsulinemia is actually an initial response to this endotoxin, and it's beneficial because it's diverting resources to the immune system because the body thinks that it's under attack. So you want the immune system to be activated, and insulin is part of that process. So here, this is just another brief map. So if we look at the top, endotoxemia definitely increases glucose-stimulated insulin secretion coming down. This increases insulin, and part of that is to divert nutrients to the immune system to sort of deal with this endotoxin. But at the same time, insulin is also involved in some beneficial mechanisms to try and turn off some of the negative effects that happen during this inflammatory process. So in both humans and animals, we see that oxidative stress is decreased by insulin, probably through an increased flux through the pentose phosphate pathway and increased glutathione production. And then there's also an anti-inflammatory effect of insulin mediated through the PI3K and AKT pathway. And then I know suddenly you're going to say, well, we know that if you give insulin to type 2 diabetics, it doesn't decrease inflammation. And that's definitely true. And that's because in insulin resistance, that particular pathway is shut off. So then you get a feed-forward effect of inflammation, but you don't have anything to turn off those problems. And what becomes an issue when we're trying to actually apply this to our patients is the fact that just measuring inflammatory mediators, cytokines in the blood, doesn't seem to be good enough to pick this up. So this is, again, data from the FINRISK study. You see CRP in the blue box. So for every 1 milligram per liter increase in CRP you have, one of the key sort of measures of inflammation, you only have a 7% increase in metabolic syndrome, increased risk of metabolic syndrome, but just being in the 25% highest of having LPS in the blood increases your risk by almost 250%. And this is because, going back into the mechanism, that the elevated markers of inflammation tend to be on individual cells themselves, but are not consistently raised in the plasma. But if you're somebody who's geeky and wants to try this on yourself or with some of your patients, then there are labs that do this, and I think that's something we can use to sort of tease this out. So hopefully I've convinced you that this is part of an important problem, and maybe why some people are struggling on a low carbohydrate diet. So I think we should talk about some strategies to then improve this. And everything I could find that fixes insulin resistance also fixes endotoxemia. And I hopefully convince you that maybe the inverse is true. If you're fixing endotoxemia, you can also fix insulin resistance. So I'm actually going to start with gastric bypass, and I don't think it's something, it's a drastic late stage measure, obviously, but if you look at the literature, gastric bypass is probably the fastest way to reverse metabolic disease, and through a number of different mechanisms, and at least one of them is probably due to endotoxins or bacteria in the gut. So this is a nice study, but this is before and after gastric bypass, and they didn't look at endotoxin, they looked at bacterial DNA in the blood. So this is bacteria that are getting across into the blood, and you can measure their DNA circulating. It doesn't bind to quite the same receptors. It binds to TLR4, but has much the same downstream effect. And what you see is the red box here. These are people who went from bacterial DNA positive before surgery to bacterial DNA negative after surgery. And it was in this study, only these people saw a decrease in their insulin resistance after gastric bypass. If we look at other studies of gastric bypass, we'll see an increase in microbial diversity. There's definitely a decrease in gut permeability, an upregulation of tight junction proteins, so reducing the amount that these bacterial toxins can get across the gut wall. And we know that gastric bypass is very good at improving incretin secretion, and GLP-2 is an incretin that's really important for gut permeability. That improves. And you can also look at just levels of endotoxemia, and they improve after gastric bypass too. So metformin, obviously a very popular drug to try and improve insulin resistance. They say that the benefits of metformin are confounded by increases in beneficial gut bacteria in type 2 diabetics. So that's, again, Akkermansia, bifidobacteria, all those butyrate producers, all those increase in people who are taking metformin. It also suppresses TLR4 signaling, so if LPS or endotoxins do get across the blood, it suppresses the inflammatory effect that they produce, and it also directly decreases endotoxemia. So again, this is in mice, but you either have them on a standard low-fat diet or the mouse high-fat diet, sugar and lard. And if you give those metformin, then actually you completely normalize the amount of endotoxin in the blood, and with that comes an improvement in metabolic health. So another one, which is an incredibly important tool, which thankfully more and more people are using, is fasting. And this goes back to that gastric bypass study. And before they went for the bypass, they had a period of fasting for about 3 months. It wasn't true fasting. It was one 400-calorie meal a day. But again, before surgery, the only people who had an improvement in insulin resistance, even though all these people lost weight, were the people who went from bacterial DNA positive to bacterial DNA negative during the fasting period. So again, fasting is reducing the translocation of those bacteria across the gut wall, and that's reducing this inflammatory response, reducing insulin resistance. And I think this is one of the important but maybe under talked about benefits of fasting. So another thing that whenever somebody comes to us and they're failing on a low-carb diet, we always want to look at their diet, and I think making sure that you're eating real food is really important. So meat, fish, eggs, various types of plants, and staying away from low-carb bars, emulsified fat bombs, and protein chips, which is what a lot of people tend to eat. And I've taken the name of the manufacturer off this because I have no interest in naming and shaming, but this is the ingredients list of a keto cinnamon bun. And even though there's no refined carbohydrate in it, if you look at the rest of the ingredients, these are basically just the things that got you in trouble in the first place. So if you're struggling to fix your metabolic disease and you're on a low carb diet, then these don't really deserve to be in your diet at all. And then we'll move on to what I call extreme measures. And I really hope that the doctors Unwin didn't bring their pitchforks, because it basically involves listening to these guys. And I talked about context initially, and though we may not always agree with how these guys treat their patients, I don't think we can disagree that they are helping them. I don't think they're lying about that. And I think one of the reasons where if you shift somebody onto a high carbohydrate, low fat, plant-based diet, but definitely whole foods, so none of like vegan chocolate bars and things like that. So I think there's two main reasons why that could help in this scenario. So if you remove refined sugars, remove refined fats, you reduce those vehicles that increase endotoxins crossing the gut wall. But then also some of the resistant starches, various types of fibers, and a lot of plant polyphenols can basically force a change in the gut microbiota, which can then allow you to shift back, if you do that in the short term, allow you to shift back to a more sustainable, maybe low carbohydrate type diet. And this is just an example of that. So this isn't a vegan or plant-based diet, but this is on a prudent diet. They took 8 people and they either put them on a Western diet, increased their endotoxin levels, put them on a prudent diet, which is a whole foods-based, low-fat diet, and again, their endotoxin came down, and that was associated with a decrease in the inflammatory cytokine TNF-alpha. So there was definitely a decrease in endotoxin and a decrease in inflammation associated with that. But actually, what I'd really like everybody to do is sort of integrate away all of these tools and use them only when necessary. So this is what we like to do at Nourish, Balance, Thrive. And we often start by looking at the gut because that's something that people tend to struggle with and I think is really important when low carbohydrate diets are failing. So this is just somebody who we saw this week, 48-year-old oncologist, competitive figure skater, is actually actively investigating ketogenic diets for cancer, so switched over to a low carbohydrate diet for their own health, and then saw a dramatic increase in fatigue and decrease in performance. And if you then look at the stool on the left-hand side, you'll see no bifidobacterium, so that definitely suggests there's going to be an increased permeability of the gut wall, and also an increase in Citrobacter, which actually has an LPS, a lipopolysaccharide, that's 10,000 times more inflammatory than the E. coli LPS that we use experimentally. So then if you're actually trying to treat somebody who's failing to respond to a low carbohydrate diet, I think testing the gut, identifying any potential pathogens is important. Supporting a better gut microbiota is important, and you can do that through diets, probiotics, prebiotics, or lifestyle changes. And you need to fuel appropriately. That's also important, and that will be based on the activity of the person as well as comorbidities. So we see some infections respond really well to a ketogenic diet, maybe overgrowth of certain clostridial species, but then some people do much better with some more carbohydrates, maybe certain other infections, particularly viral infections. And we actually talk about this a lot because we find by the time people come to us, just fixing the diet isn't enough. So fixing the environment is really the basis of all of this. And that's movement, sleep, stress, social connection, all of that. If we fix the diet without fixing those things, we really don't tend to see the benefits that we'd like. So just in summary, I think I've hopefully shown that endotoxemia contributes to metabolic disease, generally associated with a Western diet, which then causes a shift in gut function and the gut microbiota. And though I haven't talked about it today, I think eating a traditional Western diet and also doing very high volume aerobic exercise can then also increase endotoxemia in athletes. And I think that may be one of the reasons. There's evidence to suggest that may be one of the reasons why there's a U-shaped curve of exercise in terms of volume, because LPS actually contributes to some of the cardiac problems in very high volume athletes. So I think we've also shown that interventions that reduce endotoxemia also improve metabolic health, which is why it's something you should think about. And a high fat intake may actually exacerbate endotoxemia, which could contribute to the failure of a low carbohydrate diet. But this does depend on initial and current gut health, so this is definitely not definitely doesn't need to be looked at for everybody. And there is a genetic component, so we know that after giving somebody LPS, there's a genetic component based on how much they respond. So that's worth taking into account as well. So just quickly like to make a couple of thanks. On this particular project, I've done a huge amount of, or he has done a huge amount of research. Dr. Gudmundur Johansson is he's an ER physician in Iceland. Also, a lot of input from my friend Rob Hansen, who's an anesthesiologist in California. My fiance, Elizabeth, who is our chief engineer, who's made all the nice diagrams that I showed you. I'd also like to thank everybody I work with at Nourish, Balance, Thrive, who without them I really wouldn't be up here. And then I'd obviously like to thank all of you for two reasons. First of all, there are a number of people in the audience whose work has been absolutely instrumental in me getting to where I am today, doing what I do. And then also thank you for listening.
Thanks, Tommy. Okay, stretch for a couple minutes.